Hi everyone, welcome back to Hackerrank series, and we are in the 1 month prep kit in the third week. And today we are going to do this question called Sherlock and the valid string. I read this question and I tried to just understand it a little. And I've actually done this question before. So this is a quite a tedious question. And if not, like it might seem like a very confusing way of looking, like if we don't get the correct way of looking at it, we might end up doing a very inefficient code. And that's what I would like to share. That's why I would like to do this question in front of you guys and just share with you. So let's just jump straight into it. Sherlock considers a string to be valid if all characters of the string appear the same number of times. It is also valid if you can remove just one character at one index in the string and the remaining characters will occur the same number of times. Given a string S, determine if it is valid. If so, return yes, otherwise return no. So I'll just run through the question with a set of few examples. So there's A, B, let's say this example, which is ABC. There's one A, there's one B, and one C, hence this is correct. In this example, there's one A, one B, and two C's. If we just pop one of the C's, it's correct, and hence this also works. But in the last case, which is A, B, C, 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 even if we pop one, we still have two C's while the rest only have, whereas only like one. So in that case, this is not valid. So if we were to before we jump into coding, let's just try to see what are the different valid and invalid circumstances. So let's say we, on first glance, like without there's no way to get around this. We have to find the count, the frequency of each letter. So there's A, B, C, D. Let's say there's a permutation of many different many different types of permutations. And what we're doing is we just assign a value, like let's say there's two A's, two B's, and two C's, and three D's. Now this would be valid because we can just pop one of the D's and it'll become two. How about 1, 1, 2, 2? For this, even if we pop one of them, we are left with an odd like there's still 1, 1, and a 2. It's not such that all of them are the same frequency. So we cannot proceed with this, and hence this would be wrong. Well, this is correct. Another combination that we must take note of is, let's say this 1, 2, 2, 2. In this case, we don't need to pop the one at the back, but if we just pop this, we are left with something that has equal frequency. Like each character has the same frequency. And that is what we want. I mean, sorry, all characters have the same frequency. So this is also correct. So we need to accommodate this type of pattern as well. Now, how do we achieve this? Let's go step by step. Let's not jump the gun and punch a bubble, like bite more than we can chew. So what I'm going to do first is I'm going to find a way to build a frequency calculator. Like that means I need to get a way to count the frequencies. And I feel like in this question specifically, there is a shortcut, which a lot of people, like I saw some other solutions, but like how others tried to do it. It was not the best way, in my opinion. In this question, they have been quite nice to us, and they told us that all the items inside the string will be a small letter, and they even give us a hint with the ASCII thingy. So if you guys haven't gotten the unsure of what my approach is, I'm basically creating an array, and since I know there will be only 26 items, I just create an array of size 26 with 0, each index corresponding to a alphabet. So index 0 corresponds to A, and so on and so forth. Why do I do this? The reason is because if we can limit the scope to just 26, we can do the most inefficient traversals and it will still be fine because it's only 26. It's not like a 10 to the power of 5. So what I'm going to do now is I'm going to traverse through the string for I in S, and I'm going to find the ASCII number. So to find the ASCII number, we just need to do this. So if it's I, it'll be 97. Sorry, if it's A, it'll be 97. I'll just minus it by 97. So like, let's say I have a string like this, A, B, C, E. So A will be 97. I minus 97 and it becomes 0. And I will change the value in index 0 over here. So something like this. ARR ASC plus equals 1. So by doing so, I am at the end of it, I will just have an index. I have array with 26 items, and it looks something like this. I'll just print it out to visualize it. So the input over here is A, B, B, C, D. So I have 2, 2, 1, 1. Now, what do I do with the rest of this? Since it's only 26 items in the array, I can choose to do very inefficient coding, which is I'm just going to use the filters and the list and sort whatnot. I'm going to do this. So ARR is equal to filter ARR, sorry, filter lambda, sorry, my gosh, sorry, x is not equal to 0. That means if it is 0, I'm just going to ignore it, because the only case whereby we will have a 0 in the thing is if it doesn't exist in the string, in the input string. If that item doesn't exist, only then will we have a 0 in the array. So we can just remove all of them. I'm just going to use a filter lambda x. If x is not equal to 0, I will keep it, and I'll put ARR at the back. Next thing that I want to do is I need to make this into a list. And lastly, I'm going to do something a bit different. I'm going to sort them as well. The reason why I sort it out is because, okay, maybe instead of ARR, I'm going to use something else. I'm going to use final, and I'm going to print it out, print final. So let's run this. Now I have 1, 1, 2, 2, which is something like what I saw over here. Like I have arranged it and I have sorted them, because this is a really good trick for us to use. Since we have very few items after the filtration, a sorting algorithm doesn't cost us much time complexity. It's quite an efficient code on its own. So what I'm going to do now is, with 1, 1, 2, 2, think of the conditions again. It will return yes if all of them are equal. So in this case, not all of them are not equal. And the reason why I sorted is because if you look at this, the condition that they gave is to remove one. They didn't say add or remove. That means we can only remove things. If it is add, we have some other troubles in our mind. But since they have narrowed our scope by saying it's only remove one occurrence, the only place where we would ever have to remove is from the largest item. Since I sorted it, I can just go to the last index and then just remove one item from here. So the first check that I'm doing is, without any removal, without anything, is it equal? Is all of them equal? If it is not, I'm going to remove one item from the back and I'll see, is it equal now? And in this case, even if I remove one, it'll be 1, and it'll be 1, 1, 2, 1, which is not equal. Hence, it'll still be wrong. And a last ditch effort, let's say, okay, in this case, this is wrong. Like there's no coming out of it. But there will be some other questions where we would have something like this: 1, 2, 2, 2, 1, 2, 2, 2. Yep. In this case, this would be true if we remove from the front. So we can just and remove from the front only works if it is 1. If it is a 3 or something and we remove from the front, I guess that works as well. Oh wait, if it's a 3, it wouldn't be at the front. If it's a 3, it will be at the back, right? Like if the first, like let's say, because I'm sorting it, that's the benefit of sorting, because the largest item will be at the back. And if we benefit from removing, it will only be at the back. So if it's something like this, we can just remove this and make it into a 2 and it's all equal. But what if it's something like this? In this case, we need to remove from the front. And the only time when removing from the front will be beneficial if it is 1. Like no other case, like absolutely no other case whereby if you remove from the front, it helps. Because let's say if it is 2, 3, 3, 3, removing from the front will just make it worse. It'll become 1, 3, 3, 3, which doesn't help. We need to remove this. So in that fashion, we just need to make sure that if it's 1, we just pop it out. We just cancel it. And that's how we get it. So this is the grand logic of all of this. So let's get to coding it out now. We have successfully narrowed it to this. And from here, we need to do the subsequent layers. So how do I make sure that there's only one distinct item in the list? So to do that, we can use this trick, which is len set. So set is not a very efficient code, but once again, we're only dealing with things that are lesser than 26 items inside the list. So we can just, I'll just set the final. So whatever final that I got, I'll set it and it'll remove all the repeated items and it'll just be left with the base, with just the distinct values. And if I do a length of it, I should be getting 1. If it is 1, I return yes. Now, so let's go step by step. If it is not, let's say if I don't succeed in the first try, like I just try to find the distinct items and I don't get 1, I go to the next one, which is elif. And in this case, I'm testing out something a bit more specific, which is I'm going to pop the first item. Like if I just delete the first item, does it help? That's what I'm going to check now. Because if the issue is with anywhere else, so it's something like this. Len set final 1. Because I know that, like, let's say if I just kill the first one, does it help at all? So, if I kill the first one, sorry. I need to make sure the first one is a 1 first. Like if the first item in the index, final index 1 is equal to 1, and final, sorry, my bad, len set final. That means I'm assuming if it's like I'm doing 2 checks over here. First thing is if I just ignore this and I just look at the rest, is it equal to 1? If it is equal to 1, we can safely say that if we can just deal with the first one, we are good. And we can only deal with the first one if the first one is a 1. So if both of these conditions are met, we can return yes again. Okay, let me just clear all the annotations. I feel like it's a bit messy now. So the first index is 1, and the length of the set of the rest is equal to 1 as well. In this specific condition, it will return yes. And lastly, something like this. Final last index, I am going to -1 from its last position, like whatever is the last item, like in the 1, 1, 2, I'm killing it to 1. And if it is like this, I will return yes. If final, sorry, len set final equals to 1, return yes. Else we can return. So if it doesn't, if on the from the get-go, if it is not the same, and after popping the first item, it's not the same, and after deducting the one from the highest element in the list, it's not the same, we can be rest assured that there's no way this is a valid string, and we can return no. So let's run this now. Hopefully it works. I hope I didn't make any mistakes. Okay. So let's submit the code. Wonderful. I love to see the greens. The only greens I like to see, not vegetables. Yeah. Okay. Anyways, in this question, the trick, there are a few layers of the trick to the question. The first layer that I'm shaving a lot of time is by doing this, by reducing the scope of the question from 10 to the power of 5 to just 26. I just have 26 items to look at now. And this is the most time complex part of the question now. Like we don't need to worry about anything else. And this is only possible because they have narrowed our scope to this A to Z, small letters, and they even gave us the ASCII to just like help us out a little bit. So that's the first layer, and this will run in a O(n) time complexity, like however long the string is. And the rest of these operations, these are just playing around at 26 characters. It doesn't matter how complex the algorithm gets because it's a really small list to traverse now because we have narrowed our scope to 26. And after this itself, we have narrowed it down to like however many items that we have seen. So if there's only like 3 distinct items in the string, the final will just be a length of 3. So you can even do like you can do as many complicated algorithms. Nothing like what I'm trying to say is I've scoped it down such that even if my algorithm is inefficient, it will work in a very efficient manner because my scope is just it'll still pass the test cases, the requirements of the test cases set for us. So yeah, I love these kind of questions, and it's not very often that we get to see something like this. A lot of the questions that I saw did a bunch of very complicated way of going about filtering, or like they don't do filters. They went something like storing it in a dictionary, all the counts and storing all the independent values and etc., which might work, but you need to really shave a lot of time complex operations in many different locations. So yeah, work smart, don't work hard. Hope you guys enjoyed the video, and I'll see you guys in another video. Thank you.